How does a C# record validate itself? That question I had to answer 100 times in a row, so here is the video that will put all those answers in one place. I will give you the 50 shades of grey of record validation in C#. It will hurt, but you asked for it. Is this record instance valid? How about this one? Is it valid too? What's the difference? Alright, the first rule of records validation in C# is that the records are just values. And a value doesn't know whether it is valid or not. How can an integer tell if it is valid or not? Is a negative integer valid? How can it tell? So this tag record, whatever it is a tag with an empty GUID good one? We must ask the object that contains it to say. That is the first lesson you should learn about record validation in C#. Don't. Leave validation to the object that contains the record instance. That object will know more than the record knows. We might be using tags when modeling machines. Each machine requires a tag, so it rejects an assignment of an empty tag. The record itself doesn't know whether it is valid or not until we put it into another object which knows more. A different context would see it differently. A spare part might or might not have a tag. That is the request. Therefore, it will accept any tag instance. But here is the detail that will make your head spin around. There could be an interface that mandates the existence of a tag. Both models will implement that interface. That raises the million-dollar question. Is the tag instance, which is empty, valid or not? I'm not going to give you the answer to that question. Figure it out for yourself. Here is what makes that question hard. An extension method more general than any concrete machine or its part, but which knows the difference between tags the same way as machines do. This extension method is yet another context, and it defines validity in its own way. It even forgives invalid objects. It counts the valid ones. Testing, unit testing, could be another context, the fourth one. Serialization to JSON is the fifth context. The record itself could offer a helping hand with all this mess. These static factory methods make it easier to instantiate valid objects when we know what valid means. I will try creating tags both ways, as well as machines and spare parts with all kinds of tags in them. I have prepared some utilities that make testing these factory lambdas easy in this demo project. That reminds me, if you want to see the source code, it reminds me that you can see the source code by becoming a patron. Join the growing community of sponsors of this channel on my Patreon page. That will give you access to the source code of this video and 100 other videos on my channel. You can also join me on Discord, which is free, where you can take part in discussions about C# and .NET programming. You will find all the links in the description of this video. Now here is the crux of what I was telling you about the validity of tag records all this time. The only invalid tag was an empty one used in constructing a machine. All other combinations of objects are valid. I rest my case. The tag record cannot validate itself. If you wanted to add validation into it, that would be a design flaw. But that doesn't mean that records will never validate themselves. This machine could be a record, and then it would be validating the tag. Some records are true models with more meaning than just a value. Here's another example. I use strings to model the person's first and last name. But I know that empty strings are not valid inputs here. I have a great idea. why not model the non-empty string explicitly? If I had a record that guarantees that it will always contain a non-empty, non-white space string, I could model a person with no additional validation. Building larger models out of smaller ones is the principal method of functional programming and functional modeling. The non-empty string record must validate its input now because it adds a restriction to a common string. To validate a class parameter, define its property explicitly. Then take the class parameter from the primary constructor and assign it, but with validation included. I can now guarantee that any reference to a person record you obtain at runtime will be valid and contain the two strings that are truly not empty and not white space, on top of being trimmed with starting and ending spaces removed. I can even add an implicit conversion from a non-empty string to a common string. The reverse conversion from a string to a non-empty string instance might fail because not all strings are also non-empty strings. So we should not define an implicit conversion for that. But an explicit one would be fine. You can also add any transforms that will make this record more useful in the rest of your code. For example, a method that turns a non-empty string into an uppercase non-empty string. Here is the game. Once you obtain an instance of non-empty string, that instance and everything you create from it will always be valid. There will never be an invalid object if you have a reference to it. Here comes the demonstration. I will play with some empty and non-empty raw strings. The run will show that the non-empty string validation works fine and prevents the creation of an invalid person object. It is important to note that in none of these examples it was the person constructor that failed. It didn't have to. It wasn't even invoked when the error happened because I failed to construct a non-empty string record. The next case I want to draw your attention to is performance optimizations that may affect validation. I may want to model money and currencies. The currency record combines the validity of the non-empty string with the corrective action of turning any currency symbol to uppercase before use. Neither currency nor money require any additional validation in this model. Any attempt to start from an invalid, unacceptable raw string, then build the non-empty string, then put it into a currency which is part of the money object, all that would fail early at the first step. There will never be an invalid instance of any of these records. This demo is showing how you can build complex types without validation, but still the types that will never lose their safety. They will always be valid by design. But a programmer's mind is the devil's playground. A programmer may ask why we use a reference type currency that only contains another reference type non-empty string, wrapping the string reference type, all that inside yet another reference type money. And it was the string we wanted. You may be laughing at my face if I told you that all this is because I wanted them valid. Someone might want to reduce garbage collection by turning this record into a read-only record struct. But you must be aware of some pitfalls of this approach. First of all, a struct always has a default constructor. I can instantiate money with no currency at all. This must never pass, but it will. I will plug this hole by implementing the default constructor that always fails. But there is one additional possibility, the default keyword. That would create a struct instance without calling any constructor. All fields are set to defaults, including null for reference fields. Well, that is a disaster. I could offer some mitigation, like introducing a method that forces instantiation through the primary constructor. I'm carefully evading all the traps, walking on eggshells. Any use of the currency struct must include a call to this method if I want it to remain safe. Only this way will the last call also fail as requested. I will prepare the demo that tries these lambdas out and then run it. As you can witness, all attempts but the single genuinely valid one have failed. The drawback of this approach is that it is not entirely honest to me. This system of types might look safe, but it is not. The validity of objects depends on whether I have remembered to call the normalize method in all the places. Be careful if you take this route. The last demonstration I plan is constructor validation. The idea is very simple at its core. I will constrain money by wrapping it into another type with a not-so-imaginative name, bounded money. I need these constrained amounts in other models. An electronic account might allow any balance, even a negative one. A price must always be positive. But a wallet might allow 0, especially if there is wind blowing through it. I will implement these types as a discriminated union. The root record will be abstract. The concrete record types are sealed, each deriving from the base record. That brings the question of validation again. The unrestricted variant will add no validation, as its name suggests. But let's pretend for a moment that enforcing a positive amount is somehow complicated and cannot be done in the property assignment. What shall we do? You can implement the entire constructor in a record. The problem is that this constructor has the same signature as the primary constructor, so I must give up the primary constructor. Once I do so, I lose all the positional properties the compiler would generate. Luckily, there are no positional properties defined in this type. There are only the ones inherited from the base record, so there will be no damage here. Otherwise, I would have to add my own properties explicitly by hand. I can now validate the inputs in the custom constructor. The problem is that this record now allows the base records constructor to execute before validation. It would look less confusing if there were no inheritance involved. Still, implementing a custom constructor sounds somewhat irrational in records, like I didn't understand the purpose of records. Assignment validation seems more natural to me. These two records are doing the same thing, but the second one doesn't require a custom constructor. Plus, it supports positional properties, which are a great invention in record types. So you have seen all the variants of doing validation in C# records, from not doing it at all to having all the validation in custom record members. The design in between is the one I love the most. While the currency was a proper class record, these types used to be fully validated by design. There was no validation code in them, and they were always valid. I completed the validation by only carefully designing the types. Now, you may protest, saying that that is no validation at all, but it is. It is compile time validation, and the compiler is the validator. It would break the build if I attempted to instantiate an invalid object in my code. Start thinking about that.